Hey, good morning. Welcome, everyone. Very happy to see all of you here for our workshop as part of the Expanding Horizons series from the Schwarzman College of Computing. And as you know, the topic for today is all about AI and coding. So we have a really exciting lineup of speakers all the way to 4:30. And so I want to open today giving a little bit of historical perspective on where we are now and how we got here, right? This problem of how do we bring in more automation into the programming process is one that is literally as old as computing itself, right? In fact, Alan Turing, all the way back in 1945, was writing about how, in the future, all these people with, as he said, certain puzzle-solving ability would find a real home working with these computing machines, and how programming would never be boring, because the moment any part of programming became boring, then we could just automate it and move on to focusing on the not boring part, right? And it's kind of exciting that so many decades later, we're still in this active process of automating all the boring parts and actually bringing in more and more automation into this process, right? Now, for many years, this automation actually meant compilers, right? And that's how a lot of programming got automated in the early days. And in fact, when the very first modern compiler came about, Fortran, it was the Fortran automatic coding system, right? And now that we had Fortran, right, the goal is that the machine is going to code problems for itself, right? And it's going to be just as good as the human coders, but without the errors. And today, thinking about Fortran as automatic programming, right, and this idea that it automated programming and it got rid of bugs seems a little bit laughable, right? And yet, it was true, right? The kind of bugs that people were making before Fortran, right? Oh, you forget that you had this piece of data in this register and you clobbered it. Those are gone. We don't think about those anymore, right? And what this process of drawing your flow diagram in pencil and paper and then by hand figuring out how to translate that into assembly instructions, nobody does that anymore, right? That was programming back then, except now this automated tool became programming. But fast forward to the late 1970s, and suddenly the community was really starting to think more seriously about what does it mean to really automate programming, right? What does it mean to go beyond what these compilers can do for you, right? And this was the peak of the good old-fashioned AI generation, where people were full of hope and excitement, and suddenly you would be able to translate your dreams into programs. But very quickly, people started realizing that there is a little bit of a conundrum here, right? Like, yes, I want the machine to do all the coding for itself, but I still have to tell it what I want it to do, right? And especially a lot of these early efforts, how do you tell it? Well, with math, right? Because that is the universal language. That is the language that is going to allow us to have all the precision that we want. And so, pretty quickly you end up with just programming by another name, right? And as a lot of things from that AI age, very quickly it met with a lot of pushback and skepticism. There was this guy who actually won the very first Turing Award, who was very hostile to a lot of work in this kind of region of what used to be AI and eventually became formal methods, who said, well, if somebody says, I want a programming language in which I only need to say what I wish done, give them a lollipop, right? It's not a serious thing. It's not something that serious people actually actually strive for. But actually, at MIT, really starting in the 1970s and running all the way to 1987, there was this project that actually became quite influential called the Programmer's Apprentice, right? Which had an interesting take on this problem of how are we going to automate programming, right? And it's not going to be this, oh, I'm going to just use math to tell the machine everything that I want it to do and have the machine go and figure out how to do it. Instead, what we want is an assistant, right? Somebody who we can delegate the boring parts of programming, where has codified a lot of expert knowledge on how to solve programming problems, and where the user can actually direct this process of not just what do I want done, but how do I want to implement, right? And the idea was that if you could have a collaborative model, it would be strictly additive, right? Even if the system is really dumb, and even if it doesn't know how to solve a lot of problems, well, you're just doing whatever you were doing before, right? But it can help. If it can help you, then it's better, right? It knows things that you don't know, and it knows how to solve problems that you don't know how to solve. And I think this has a lot of resonance with the tools that we're seeing today and that are starting to be successful in actually helping with software development, right? And a key ingredient here is that the developer is just writing code. They already know how to write code. They're going to keep writing code, and they have this assistant on their side in order to actually help them. So, for a long time, there were a lot of questions of, how do we actually make this happen? Especially, the early 90s were a period where there was a lot of evolution in programming languages. Machines were getting much faster, so suddenly, things, much higher level languages that simplified a lot of the work for you were becoming feasible. Suddenly, people could just use libraries and to reuse code that somebody else had written. So for a while, there wasn't as much interest in this question of really how do we bring real automation into this process. And this is actually the point where I started my PhD, looking about 20 years younger than I look today. And this was all the way back in UC Berkeley. And we started with this notion of, okay, so the way people are dealing with automation today is mostly with compilers, and compilers can be made very smart, and they can be made very good for lots of problems, but there's a really long tail of niche problems for which nobody's going to bother to write a compiler, right? There's just not enough of an incentive, and at the same time, the people developing code in these domains really need help. Right? And so what if you could have something that's a little bit more like an interactive compiler, where you can tell it at a high level, this is what I want to implement, and actually have it help you make sure that you're not making mistakes, have it help you figure out some of the low-level details. And so we decided to go for the nichest of niche domains, something where clearly nobody would ever bother to write a compiler for, which was bit stream programs, right? You have programs that are just manipulating a stream of data as just a whole bunch of bits, and where you might want to do things like, let's say, drop all the error correction bits, right? Or drop every third bit out of this stream. It's a task that is, on the one hand, really boring, but if you actually want to do it really, really fast, it turns out to be kind of a mess, right? And there's all these little tricks of the trade that if you know how to do them, you can make things go an order of magnitude faster, but only a few people know how to do them, right? For example, if you have something like this, you can decompose this so that at every step you're closing half the gaps in your word, and now suddenly you can do something really quickly that otherwise would take many more instructions to do, right? And the question was, could you help the programmer just sketch out how this is going to work, right? Could you have them tell you, you know, a little bit about how this implementation is supposed to look like, but by doing that, define a search space where you can go and search and find the implementation that you can prove to be correct, right? And this evolved actually into a language where the dream was that you can go and just leave holes in your code and have the system go and figure out how that hole needs to be completed in order to give you the right answer, right? This was like the hello world of our Sketch programming language, where you say, well, I don't know what I need to multiply x in order to do this, but the system can figure it out just by the assertions that I have in my code, right? And you could even do, you know, more interesting programs, like if you want to partition an array with n elements over p processors, right? Well, maybe I know that I need some operations like mod and division, and so I can sketch out how my implementation is going to look like and give a test harness that says, this is the test that my implementation is supposed to pass, and have the system automatically explore this enormous space of possible ways to combine all these operators to actually give you the code that is going to do the right thing, right? And these days, when I talk about this kind of work, I sound like an old person talking about the good old days, you know, back before we had all these fancy technology. But you know, this was the state of the art about 15 years ago, and it enabled us to really start thinking in terms of, you know, what could you do if you actually had the ability, if you actually had a system that is able to write code for you, right? But this also coincided with the rise of deep learning, right? And but even before that, right, suddenly the community started realizing that, hey, if you have this ability to generate even relatively little pieces of code, you can actually do some pretty useful things, right? Even if you're not able to actually go and help software engineers trying to build massive software, right? For example, a lot of end users, they have to do things with their computer that are actually much better solved by programming, except maybe they don't actually know how to program, right? And so having this ability to say, well, I have all this data in my spreadsheet, and here's some example about how I want to extract that data. So this was a system called FlashFill that eventually made it into production. This was developed by a researcher named Sumit Gulwani in collaboration with actually one of our students here at MIT, Rishabh Singh. And suddenly, you could actually just help people who are trying to get stuff done in their spreadsheets by going and synthesizing little programs in the background that match the examples that, that they provided, right? But it was really the advent and the growing power of deep learning that really made it possible to push a lot of these technologies to the next level. So all the way back in 2016, we actually started in 2015. Our colleague, Regina Barzilay, started talking to us about these newfangled sequence-to-sequence models, right? And the possibility of using these new language models in order to actually help us write code. And at the time, we were actually really interested in this problem of how can we leverage the ability to generate code to help students who are trying to learn programming. This was also the beginning of massive open online courses becoming very popular, and so suddenly we had access to these big data sets of programming assignments and the solutions submitted by students from all over the world, right? So the idea was, what if you could train a language model to actually infer the solution to one of these programming problems, right? And not only that, so the idea was that you could train a language model to look at the context around a line of code and then predict the line of code in the middle, right? And if you train the model like this, right, just to predict the line of code in the middle with all of these data that you have coming out of these massive open online courses, right? Now, at testing time, right, some student goes and writes some piece of code, and there's a little bug in this piece of code, right? But now you can use your model and make predictions about what should the line of code there in the middle look like, right? And the model can actually identify that the line of code that the student wrote looks very different from the line of code that the model was predicting, and therefore, given that this piece of code doesn't work, maybe we want to go and highlight to the student that there might be a problem here about the code that they are developing, right? So this was actually a really early instance of showing how language models trained on large amounts of code could actually be useful to write code, and in this case, for people who are trying to learn how to program, right? But this was the point where the technology was moving very, very quickly, and suddenly we had attention, right? And this was a group of Microsoft. Rishabh was my student who had recently graduated from our group. And they started experimenting with, hey, there are these newfangled models based on attention. Turns out you can use them to generate some of these text manipulation programs automatically, right? Much more robustly than a lot of the symbolic techniques that we had been using up to this point, right? This was really the first instance demonstrating the use of attention to generate code and to generate programs, and showing that it could actually do better than a lot of the symbolic techniques that we had been using for many years now, right? And it wasn't too long after that when people started exploring with, what if instead of just little programs from a course, we actually go and scan the internet and start looking for all of this code that is available on the internet, right? So this paper by actually one of my collaborators, Chadhuri at the time, was trained on 150,000 samples of code from the internet, right? And you can still see how, the growth in the ambition and the power of these kind of systems, right? And the idea for this system was that it could now learn how to map from keywords and names of types all the way to code that you could actually go and run on and incorporate into your project code that would actually tell you how to use an API that you might not be so familiar with, right? But as we all know, it was really right in 2018 when this idea of pre-training language models on the entire internet that the world really changed, right? And we got to the point where we are today, where people are even starting to wonder, right? Are we still going to need human programmers in the future? Should people still be learning to code? Where a lot of these where the technology to do automated programming has left the lab and is now in widespread commercial use. But one of the things that is really interesting to me, looking back at a lot of the things that happened before that, is that software engineering has always been a really important aspect of why we want to automate programming, right? It's a huge industry. Everybody is developing software these days. Every company has to do software development of one form or another. And so automating the development of software is a big thing. But there is another side to this technology, and it's the idea that code is not just a means to writing apps and server-side applications, right? Code is the most powerful notation we have ever developed to describe really complex things, right? And you can use code, certainly, to write software. But today, if you're a physicist, you're probably writing some code, right? And if you're a biologist, you're probably writing some code, right? And if you want a model that really describes, everything we know about some metabolic pathway, right? What better way of describing it than with code, right? It's precise, it scales. And so what that means is that if we have the ability to generate code, we can do much more than just software engineering, right? All the way back in 2010, there was this really interesting paper that showed that you could actually turn this problem of synthesizing code on its head, right? Traditionally, people thought of synthesizing code as you have some developer, they write some specification, and then the machine goes and writes an implementation for you, right? But the specification itself could be a formal language. It could even be just some higher level version of the code, right? And what if you could actually just run this in the other direction? You have some big piece of code, and you want to generate the high-level description of what exactly is it doing, a human understandable representation of what this piece of code does, right? And in the case of this paper, they were actually interested in reverse engineering worms and exploits for computer system, code that had been obfuscated in order to make it explicitly hard to read. But it didn't actually take long to realize that once you have this ability to just discover what some complicated system does just by observing how it reacts to different stimuli, this could actually have effects way beyond software development. So back in 2013, a group led by my former PhD advisor decided to take this synthesis technology, as primitive as it was at the time, and actually see whether you could actually use it to discover some real biology, right? In this case, the idea was, could you actually discover something about the metabolic pathways in this worm, C. elegans, right? And the idea is that you have these metabolic pathways that control how these cells interact with each other. And internally, people represent them with these graphs that describe how different factors and different proteins promote or inhibit the development of other factors. But you can think of this also as just a program, right? You can represent this as a piece of code. And now you have experimental evidence that shows how this program reacts to different stimuli from the environment. And so now you have a program synthesis problem where you're trying to figure out what does the program look like that is going to react in this particular way to all of these different stimuli, right? And not only that, you can actually do things like generate multiple hypotheses consistent with the data, that all of them fully capture the data, but that might behave differently in the context of different stimuli. They might behave differently when you knock out, for example, one of those proteins. And so this ability to actually generate models of the world that not only are capable of making predictions, but allow for the possibility of introspection, allow for the possibility of analysis, allow you to actually design experiments for to test these competing hypotheses that are all equally plausible, given the observations that you have made so far. Actually, in collaboration with Josh Tenenbaum, who's sitting right there, and Tim O'Donnell and Adam Albright, our student Kevin Ellis did some work a few years ago where he took this idea and looked at, well, could you do the same thing for language, right? Could you actually take these observations about just words in a language and figure out these morphology and phonology rules, for example, that in the case of English, tell us that if you want the past tense of open, you're going to say opened. But if you want the past tense of work, you wouldn't pronounce it as worked, you would pronounce it as worked. And can you actually reverse engineer those rules purely from those examples, right? And suddenly you have a domain here that looks nothing like software engineering, but where having this ability to generate code that matches a certain set of requirements, having the ability to actually explore a large space of programs gives you this ability to generate these interpretable models that allow you to do introspection, that allow you to gain real human understanding about what's going on, as opposed to simply making predictions. So, looking forward, machine programming is here, right? There's no question about it. Programming today already looks very, very different from how programming looked like a year ago. And chances are, 3 years from now, programming is going to look very, very different from how programming looks today. And for the rest of the day, we're going to be seeing a lot about where exactly these technologies are going, and a lot of the different ways in which also research contributes to pushing that boundary forward in terms of what these technologies can do. But I also ask you to keep in mind that program automation, right, and this ability to generate code is actually going to open a lot of opportunities that go beyond just the question of how do we make software engineers more productive. This is truly a key capability that can help us really improve our understanding of the world. And so with that, are there any questions?
One of the problems of getting a programming system correct is that you don't always know at the beginning what a specification is. It very often needs to have an interactive process where the user sees something and says, this isn't really what I want. How do you incorporate that into this?
So this was actually one of the big challenges that a lot of this early work on program generation ran into, right? That it was operating from this idea that somebody already knows what the program is supposed to do, and they're just going to write the specification, and out is going to come the code. Nobody at the start of a project knows what the software is supposed to do, right? You are, a big part of developing software is this process of discovery. What is it supposed to do in all of these different cases? And I think a lot of the value that we're seeing with some of the modern tools, first of all, being able to actually prototype things very, very quickly, right? To be able to shorten those cycles of actually trying things out, right? It used to be that if you wanted to mock up some functionality, that still took you a fair amount of time, and maybe you actually do some pieces with pencil and paper just to see how they work out, right? Today, you can actually go through these cycles very, very quickly. I think another aspect that is really interesting about how these tools are influencing development today is that a lot of development is actually not that original, right? In a lot of cases, people are just trying to get the software to do the same thing that lots of other pieces of software already do, right? And so this means that the models actually have fairly strong priors over the things that you're actually most likely wanting to try out. But I think, when people start going further and talking about, well, are we going to actually need developers at all? I think this question is central to why I think we are going to need humans to be an integral part of this process, right? Because ultimately, somebody has to decide what is it that this piece of code actually is supposed to do.
I just wanted to ask, does the representation matter, like as simply as which programming language or this giant array of numbers, et cetera? Feel free to interpret that however you think is most interesting.
So this is actually, I think, a great segue to Daniel's talk a few minutes from now. So at risk of stealing his punchline, but yes, I think representation is going to matter a lot, right? And right now, Python is a language of convenience. It's there, everybody uses it. There's tons of data out there on how to write Python code, and so the models are really, really, really good at writing Python code, right? And but a lot of programming languages today are trying to navigate a trade-off between how difficult it is to write the code and how difficult it is to read the code, right? And suddenly we have the opportunity to actually escape that trade-off. So I expect to see a lot of exciting work in that direction of notations for how do we actually write code now that we have the machines helping us with that.
What are the skills today and in your hypothetical 3-year time point that will distinguish a good software engineer from a bad software engineer? And I guess from that we could maybe figure out what should a software engineering degree actually try to teach. So what does and what will make a good software engineer if ChatGPT is doing almost all the work?
So this is a really good question, right? And one of the big challenges that we have with this technology is that anything you can quickly test, you can train these models to do really, really well on, right? And the problem is that the things that you can quickly test are also the things that we love to teach in our programming courses, right? Because we can quickly test them and tell who did it right and who did it wrong, right? And the kind of skills that are very difficult to put into these models are the skills where the feedback loop is very long running, right? If your code has the wrong structure and the wrong design, you might not realize that until 2 years down the road when you're trying to implement a new feature and you realize that you have to change everything in order for that feature to work, right? Or when you're bringing in another batch or you're doubling the size of your team and now none of the new people understand what's going on in your code, right? And so some of those skills that have this very long feedback time, those are the ones that are going to be pretty hard to automate with this technology. And I think those are the ones that we need to figure out how to teach them better to our students, despite the fact that they're, by their very nature, they're not so easy to test in a multiple choice quiz. Not that we ever do multiple choice quizzes here in Core 6, but.
Yes, would you mind giving a few examples on your last sentence on your last slide right there? Automation opens opportunities beyond software development. Any thoughts on what
Yeah,
those might look like?
so to me, one of the most exciting areas is in this space of scientific discovery, right? Where there's a lot of domains where, yes, you have a lot of data, but you don't have enough data to actually cover all the cases, right? And not only that, right? The hallmark of a good scientific theory is that it should allow you to make predictions beyond the data that you used to figure out the theory, right? It should allow you to introspect on the theory and figure out, new experiments and new tests that can actually test those corner cases of the theory that your existing data that you used to figure out the theory doesn't cover, right? And so having programs as a representation gives you a lot of power to do exactly that in a way that, just having training models to learn how to do make some prediction is not going to give you.
I will get to the second part of my question soon, but I'm kind of reminded a little bit about Ruby on Rails, where 3/4 of the work was coming up with a test set to verify that your program was actually correct. And I think that may be one of the big challenges for AI, how to do that. The other problem I run into with a lot of these do what I mean systems, like spelling correctors, is that if I misspell something slightly, I will get an essay totally different from what I was trying to write, even on something as simple as a piece of email. And that gets even worse with programs, that unless you go back and have some good means of verifying things and or take the time to review it, you may end up with a program that does something very different than what you really wanted. And that gets aggravated if you have third parties with other interests, like someone who wants to infiltrate a system by making small changes to the code that allows them to do something else, or otherwise get you to do something otherwise than what you intended.
Yeah, I mean, the quality question is a big one, right? And especially as the systems get better, and even when they don't actually know what you want or what you're trying to do, are doing a good job of producing plausible solutions that look like they work, even when they don't, right? And I think this is one of the important frontiers in the space, is how do we get these models to reason more rigorously about correctness, but also there is an interaction question, right, of how do you actually convey those non-negotiable properties that you absolutely need the system to maintain, for example. So I think this is a good time to stop, and thank you very much, everyone, for being here. And I want to welcome Daniel Jackson, our next presenter for today.